So today I'll be telling you about tuning transient jamming in dense suspensions by means of encoded memory. Okay, so what is a dense suspension? So if we take a liquid and put some solid particles in high proportion, we get a dense suspension and they show amazing force response. So these are few examples. So this is a dense suspension of constant cornstarch particles in liquid, in water, both of them, in fact. So you see, like if we is a liquid like at rest. So if we drop a heavy object, you see that rather than creating a splash, actually, it becomes a transient solid and it can bounce the ball, which is like 5 kilogram ball of the surface. And you see under extension also it behaves very differently from a conventional liquid. A few years back, we actually showed that these all these properties come because of shear induced jamming transition. So this is a pure shear geometry. So you have a cylinder that is rotated, it can spin, and you have a beaker. You keep this suspension inside that beaker, and by spinning the cylinder, if you rotate it fast, you can see that you can make it like a solid transiently. As soon as you stop shearing, it will sink. Okay. So because of this property, it has like many important implications. I'll not go into that. So now today I'll be telling you about this memory formation in these materials. So we know that out of equilibrium amorphous solids like glasses and all, they show memory effect, like Kovacs effect and memory of amplitude in glassy material. There is this recent review of modern physics paper. So, however, like in glassy material, the relaxation processes are very, very slow, stress relaxation and other type of relaxation. And they also have residual stresses. So if you apply a perturbation, so stress doesn't go to zero even after a long time. However, like I showed you, the system showing shear induced jamming, that is a very different type of system because the stress relaxation is very rapid. If you remember the movie, that when I was shearing, it was turning into a solid, but as soon as it is stopped, it is going to a liquid. So it is the stress relaxation, it is going from solid to liquid like very, very quickly. So fundamentally, these systems are very different from this glassy material. Okay. So, so this is our experimental system. We synthesize these colloidal polystyrene particles in large scale in our lab by technique called dispersion polymerization. So they are fairly monodisperse and it is very weakly Brownian. The size is 2.7 micron. We can vary the size, but for this talk you can ignore the Brownian motion. So this is the experiment basically. So what we do, we take a dense suspension, we apply a transient perturbation in the form of a step strain. So you take the suspension, you apply a sudden strain, step strain, and then you observe that how the stress relaxes. By stress, I mean the bulk stress that is measured by this rheometer relaxes. So as I told you, if you do this experiment, you will see that stress reaches to a peak as the material solidifies, which is very high, and then it fairly quickly it relaxes. So this is a actual experimental data. So this increasing part is not shown, so it is very, very rapid. And then you see that within typically 1 second, 1 or 2 seconds, it reaches zero, and it involves like 4 orders of magnitude relaxation of stress. Okay. So now, what happens if we continue this experiment? That we apply a step, let the system relax, then we apply another step. So what happens then? So intuitively we would guess that, okay, so since it is relaxed, the stress is relaxing to zero, it is a liquid-like state. So the system doesn't have any memory. So if you load it again, it will probably you get almost similar behavior within experimental error. So now this is what we find. If you do this experiment in the lab, and please note that this time of all these steps, this we varied over large range. So this is for 5 seconds, but we have waited for 10 minutes, 15 minutes, whereas stress relaxation is just a few seconds. So you see that if we do this experiment, this data is very squeezed actually, but these are those steps. So you see that, okay, you get a rapid increase, stress relaxes to 0. Next step, you see increase, it relaxes to 0. In all cases, the stress relaxes to 0, but see like the peak systematically increase, which is counterintuitive. We would have imagined that, okay, we'll get almost similar response, but maybe within experimental error. But looks like that actually, despite of this rapid relaxation by 4 orders of magnitude, any step, it remembers what happened to previous step. Actually, it increases always. Okay. So another thing we notice that if you look at very carefully what is the nature by comparing them in a log scale starting from the same point, you see that you get a smooth relaxation at the beginning, but like after application of several steps, actually develops this 2-step relaxation. And from our earlier study, we learned that, okay, so this 2-step relaxation in shear jamming system is related to relaxation of plasticity. Okay, so looks like that this training, application of repeated pulse, making this shear jam state into like making it more brittle. Okay, and we also observed the sample under boundary imaging that this is the setup in our lab because these particles are opaque. So you shine some light and then just collect the diffuse light with camera. So we confirmed that, okay, with different steps, like I told you that it is developing some brittleness. Indeed, by boundary image, if we see the images at each peak, we see that, okay, a smooth boundary actually gradually showing these plastic events which are like this characterized by bright spots. Whereas if you do this alternative training, no such effect is there. In fact, if you start with a brittle state with a lot of plasticity, it goes to a like more liquid-like state. Okay, so we are collaborating with Dr. Vinuta in Georgetown University. She is an expert in simulating this shear jamming in dense suspension. So this is a bidisparate system. This discrete element simulation. Yeah, I'll take one. So, what this Z is simply the average number of contacts of these non-rattlers. So you see that as the system is trained more, you get like this kind of contact formation between the particle. Okay, and now what she did is like if you apply multiple steps and each peak stress is shown by this point, so you see indeed there is increasing peak stress and then it saturates. Actually, this saturation I didn't discuss experimentally, but if you do this for large number of steps, indeed it saturates. So then also we can measure the average contact number between the particles. So one thing that is missing from the simulation that comes naturally in experiment is there is no relaxation in the simulation actually, because this simulation is ignoring hydrodynamics. But now, so we are working on these, like we have some idea that how to reconcile. And another interesting thing we obtained from the simulation is with increasing number of contact, this training is increasing this average Z value. We looked at the locally rigid clusters in the system, and you see that there is a evolution of local rigid region in the system, and finally this rigid cluster size becomes comparable with the system size. And so this is the conclusion. So this memory formation plays an important role in controlling mechanical properties of response of shear jam state. And there is a decoupling between structure and stress relaxation. Why this effect is happening, we think that although the stress is relaxing to 0, but you have these local clusters like which are locally rigid structure or some particular structure of the force chain. that is like encoding the memory in this system, and that structural relaxation is very, very slow. Okay, so all the experiments are done by my grad student Sachidanand, who is going to finish, and our collaborator Vinuta in Georgetown University, who visited here last week. These are the current lab members, my group at RRI, and like to thank RRI and ACRB for funding. Thank you. Yeah, I mean, so actually that existing model for shear jamming system, like it was just without hydrodynamic. Hydrodynamics can be implemented, but we haven't tried that actually. So,
yeah. On that same subject, you said there was no relaxation because you didn't introduce hydrodynamics. But if you just had, Brownian particles moving around, there's a structural relaxation time just from that itself, right? You don't need hydrodynamics.
Yeah. So if you go to Brownian regime, then you can have a competing time scale.
Yeah, yeah.
But both the simulation and our system, first of all, like these are close to 3 micron particle, and secondly, like they are very dense. So the Brownian motion is less, but you can do the same experiment. Let's say you do in 10 nanometer, 100 nanometer particle. So there, you can have that competing time scale for sure. Yeah.
Okay, so I think there is no question. So let us thank the speaker again.